Welcome to our afternoon session. This is going to be a continuation of our discussion on remote sensing of soil moisture. Our first presenter is Eshita Eva from Ohio State University, and she's going to be discussing downscaling soil moisture data to a 1 kilometer resolution. Welcome, Eshita.
Thank you. Hello, everyone. I'm Eva, so doing PhD at the Ohio State University. So today's my presentation is on identifying the optimal approach for developing a 1 kilometer downscale soil moisture product for CONUS. And I would like to thank USDA because this project is funded by USDA. So before jumping into the details of the project, I would like to talk about what motivation work behind this project. So soil moisture is a significant variable in the climate system because it regulates the land and atmosphere water energy balances through soil evaporation and transpiration. Soil moisture is also important for examining, monitoring, and for the stream flow hydrological parameters such as stream flow and flash flooding, drought forecasting, and other weather and climate forecasting. Although soil moisture is a small constituent in terms of the total available fresh water, which is 0.0015%, and the total water in the global water cycle, which is 0.05%. And it is considered one of the crucial parameters in the global climate system because it plays a significant role in exchanging water between the land surface and the atmosphere through and soil moisture controls several different processes in the global hydrological cycle, such as runoff, infiltration, and percolation, base flow. Soil moisture also substantially influences the cycling of global carbon by controlling soil carbon through the respiration process. And in terms of agriculture production, soil moisture has the influence on crop field, irrigation planning, disease outbreaks, pest control, and it also allows for irrigation to be applied before the crop is stressed. And soil moisture is also important for the different functions of the plant, such as plant photosynthesis, because when the soil is dry, photosynthesis decreases and this reduces plant growth. Soil moisture also helps to accumulate carbon in the soil, and phenology depends on the water content in the soil. While soil moisture is important for many purposes, national soil moisture products are not available with high resolution. So different products have different spatial resolutions, such as satellite soil moisture products are limited to 9 kilometer spatial resolution, and model-derived products are limited to 12.5 kilometer. Therefore, often it is not sufficient for field scale applications in different sectors, particularly in agricultural sector. Moreover, these products are not easily accessible to the farmers and to anyone. Therefore, this project will address the critical need to enhance the accuracy and utility of soil moisture products by integrating the available data sources to downscale them to different finer scalars, such as 2 kilometer, 1 kilometer, 700 meter, and 400 meter. And the downscaling will apply the artificial intelligence approach, such as machine learning and deep learning methods, and to disseminate this soil moisture data to the corner. So some previous studies that have found that the combination of multiple data sources is very essential. And also there are some missing opportunities that can help to develop the models to assimilate multiple data sources, such as satellite derived products, model derived products, and also the in situ data sets. And the main important point is here, the accuracy of the input data sets is also very important, because if the accuracy of the input data set is not good enough, then the output downscale products will also not be that good, because when we validate the models, then we need the in situ data set. So the in situ data set should be more accurate. So here are some gaps that I have identified. National soil moisture products are not available with high resolution, that I have already told. And also we need to consider consider the ancillary variables as much as possible. And also this dataset is not readily accessible to anyone, and they are not enough sufficient for the field scale application. And the research question here is that which variables are more important in downscaling soil moisture products, like land use or the elevation, temperature, precipitation. We will identify which variables it has the more influence on downscaling soil moisture products, and what would be the best approach to downscaling soil moisture data. Like we will apply different machine learning methods, then we will try to detect which is the best model, and what would be the best spatial resolution. Um, because when we will downscale the soil moisture products into like multiple resolution, then we will try to identify which resolution, like 2 kilometer is the best resolution, or 1 kilometer is the best, or it could be like 400 meter could be the best resolution. Sure. I have identified 3 objectives. First one is to determine which variables have the influence, and then the objective 2 is identify the most appropriate AI model for downscaling the available soil moisture data set, and the objective 3 is to quantify the accuracy of the downscale to determine which resolution is the best for the CONUS soil moisture products. Here is a schematic representation of the workflow that I will follow. First, I have some independent ancillary variables: precipitation, antecedent precipitation index, the temperature, maximum temperature, minimum temperature, and the DTR is data range, and land use, normalized difference rate index, leaf area index, elevation slope, and also the GSAR graded products. And I have some independent variables, which is soil moisture SMAP L3 products, and the special resolution here is 9 kilometer, and the soil moisture in situ products. So first I will apply the nearest neighbor interpolation to come up with a common special resolution, which is 4 kilometer. Then I will apply some machine learning models, random forest, support vector machine, nearest neighbor, convolution nearest neighbor, and the LSTM long short-term memory. When I will have the downscale soil moisture products, then the model will be evaluated, and this accuracy matrices such as coefficient correlation, mean absolute error, RMSE, unbiased RMSD will be calculated, and that's how we will try to answer our research question. So the next thing is the method, random forest. So random forest is a robust and accurate algorithm that can handle non-linear, high-dimensional, and noisy data. So that's why it is a considerable method, and it can also handle both categorical and continuous input features. Random forest can automatically handle missing data and can provide estimates of variable importance. So to detect the variable importance, we will apply the random forest. And it is less prone to overfitting than other machine learning algorithms, which is a merit of applying random forest than other methods. And we will also try to apply bootstrapping method, because it will help to avoid the overfitting. And then the support vector machine. So it is also a powerful algorithm because it can handle also the nonlinear data sets, and it is helpful for classification and the regression problems both. And it is like a representation of two-layered networks. And it is powerful because it helps to approximate any training data, and it also helps to generate better on a given data set. And then next, the artificial neural network. It is also powerful of a deep learning method, and it detects the relationship between input and output, and it is a consist of a set of layers, and it is crucial to determine the optimal number of nodes and layers to hide in a model, because it helps to maintain its complexity. So model complexity will increase if the number of hidden layers will be greater. And also a weight is assigned to each neuron, and the weight of each neuron decides the function of the weights. The output of each neuron will be a linear summation of the weighted inputs plus the bias that will go through an activation function. So, and on the other hand, the number of neurons in the output layer is equal to the number of outputs given to a artificial neural network during the training. And the backpropagation algorithm is widely used to train the neural network. And the next is convolution neural network. So convolution, activation, and pooling. These are the three parts that make up the basic structure of CNN. And a kernel will be used to extract the feature of the inputs in the convolution process. Then the activation function is used to make a nonlinear mapping. Then the extracted features are compressed in the pooling process. And in general, the output of the CNN is treated as the input of the fully connected neural network. And in the training procedure of the CNN, the backpropagation algorithm is conducted. So once the loss function is determined, weight and basis parameters can be optimized by some specific methods, such as stochastic gradient descent method. And the next one is long short-term memory. So it is a special kind of RNN, recurrent neural network, and it is capable of learning long-term dependencies. So LSTM are explicitly designed to avoid the long-term dependency problem. The research shows that RNN is limited in maintaining long-term memory. So therefore, the long LSTM was invented to overcome this limitation by adding a memory structure which can maintain its state over the time with gates to decide what to remember, what to forget, and what to output. And next is our data sets, in situ data sets. So in situ soil moisture is the observation of water in the soil. It is typically a volumetric water content, which is a fraction of the soil comprised of water. So, and soil moisture is measured with a variety of different sensors. So the period of record for most of the in situ measurements is relatively short, which is less than 20 years. Moreover, the stations are not evenly distributed, and there are relatively few stations in the United States. So this lack of spatial coverage and the limited period of record makes it difficult to use in situ measurement, soil measurement for national monitoring. And the next one is SMAP level 3 data. So remote sensing provides a grid data products instead of the point-based soil moisture measurements, and it provides greater spatial coverage, typically global. So the soil satellite products are available at daily to weekly resolution, and it can be considered as one of the advantages of using satellite products. But the major disadvantage is that they only provide soil moisture estimates of surface soil moisture. But for drought monitoring, the root zone soil moisture and the moisture of deeper soil layers are also essential. SMAP data are available from 2015 to present day. So our research will use the SMAP L3 as level 3 product, and here the resolution is 9 kilometer. And this version provides morning and afternoon data, but I did average to produce a daily value.
Eva, you have 2 minutes.
Okay. And this table is for the ancillary variables. So I have considered elevation, slope, and aspect, and this elevation is collected from USGS products, and then I have calculated slope and aspect from DEM data. And soil texture is data is collected from graded soil moisture, which is provided by NRCS. And NADUS data is downloaded from NLCD. So I have collected precipitation from PRISM, parameter elevation regression on independent slope models, and I have calculated API from the precipitation, and also the mean temperature, maximum temperature, mean dew point temperature. All these products are collected from PRISM, and their native resolution is 4 kilometer, and they are available from 1981 to present day, and their temporal resolution is daily, which is a advantage of using these data sets. And NDVI and LAI are the vegetation data sets, which is collected from AVHRR, atmospheric height radiometer, and their spatial resolution is 9 kilometer. And they're also available from 1981 to present date, and they're available daily. And these are some maps to show. And our next steps will be to test this ancillary variable to rank their importance and to consider different machine learning approaches. And I'll apply I'll apply these machine learning approaches to different spatial resolutions. And the last steps will be to make available these data sets through a website. That's all. Thank you.
Thank you, Eva. We have time for one question.
Do we have any questions? No? All right.
Okay, if we don't have any questions, we're going to move on because we're a little late.